So today we are going to continue again for discussing about sensor property. So last week we have discussed various causes of errors, for example, and then we discuss different terminologies of sensor performance, terminologies as related to sensor performance. We have discussed what sensitivity is and sensitivity drift, then about range, and then what else do we have discussed? We have discussed about drift, and precision, the difference between precision and accuracy. Then what resolution is, we also have discussed about it, and offset, which is can be considered as the output then that exists when it should be zero. Then we have discussed also about linearity, so how close the curve or the calibration curve of a sensor approach linear response. So then usually this can be obtained by using linear regression, where you will also obtain the degree, the coefficient of linearity, the R square. Then we have spoken about hysteresis, as explained here in this figure, where the response of the sensor is different when the input is scanned from low or small value to the larger values, and then when it is scanned at another direction, from larger value to the smaller values. So here then, when they give different response, when the sensor gives different response, it means that the sensor has hysteresis, and this is due to some energy is being lost, information is being lost. Okay, so then we are speaking about, now we continue with the dynamic response. Of course, here we have also discussed about response time, the time required for a sensor output to change from its previous state to a final settled value within the tolerance band of the correct new value. Okay, sorry, another internet glitch. Today the internet somehow is not stable. Sorry for that. Let's continue again. So in response time, it shows how fast the sensor is, when it receives certain stimuli. So when does the sensor reach a certain final settled value when an input is given? So this indicates the response time. Usually it will be the value of the 1 over tau, according to when it reaches tau, the time constant. Remember, in circuit analysis for first order system we have the tau. So when it reaches tau, or about 63%, it can be defined as a response time. But the response time can also be defined differently. For example, we can define yourself that for comparing different systems, you define response time as when the system reaches about 95% of the steady state value, for example, or 97%, depending. So it could be, for example, 1 tau. So, or after 4 tau. When it is 4 tau, usually then the error from the steady state value is already less than 2%, or 5 tau, something like that. Okay, so when comparing, you have to state clearly what is your definition of the response time. Otherwise, then different people maybe consider it differently. Okay. Okay. So besides this statical, what we call a statical terminology or statical characteristic, we also know dynamic characteristic. So this is the steady state characteristic of a sensor. How does the sensor react or respond upon stimuli having different frequencies, different frequencies respond. So a perfect linear system will have a wideband response like this. It means whether the stimuli is very slow, where the changes is not that frequent, it means that the omega, the frequency of the signal, is very small, or even a DC signal. For example, like if you consider body temperature varies very slowly. Yeah, maybe you have variation between day and night, but not that a lot of variation, maybe slight variation, because our body has our uh, body temperature regulation system. But if you consider, for example, the heart signal may contain a little bit faster frequency. Yeah, between the bandwidth is between 0 until, let's say, about 100 hertz. When you speak about muscular activity, also the bandwidth is about 0 to 100 hertz or 150 hertz. Then when you speak about neuronal activity, the brain activity, then it has even much more higher frequency, yeah, in the range of 1000 hertz, for example. So a perfect system, when your sensor is perfect, when it is used to detect this different system, this different signal, either from body temperature. Let's say all we assume that they have voltage output, yeah. Body temperature system, the heart signal, muscular signal, or the brain signal, then a linear system will have the same amplification factor for all the frequency range of this signal. But in reality, that is not so. In reality, the system usually have this kind of band pass response. So below certain low cutoff frequency FL here, then the amplification will be lower than 0.07. That is half times the square root of 2. Then it will have relatively constant amplification, constant gain when it is between the FL and FH. FH is the high cutoff frequency. Where above the FH, above the high cutoff frequency, when the signal or the stimuli has very high frequency above FH, then the amplification or the signal gain will further decrease from the value here. So this is the most of the sensor behave like this. So they have a low cut of frequency and a high cut of frequency. So when you choose a specific sensor for your particular application, or when you build a sensing system for a particular application, you have to pay attention to this bandwidth also. At which frequency range of signal that your sensor can still capture the information. Okay. So in typical sensor, this is also the response. Yeah, the phi, this is the phase change as a response. This is the signal gain, while this is the phase change. Okay, in ideally, it should be, for example, the phi, the phase should be equals to k omega, a linear amplification of the frequency related to frequency by a constant k. But in actual sensor, typical for sensor, usually it is not that linear. There's the function of phi, the phase, as a response versus the frequency of the signal. Then we have a square wave. Yeah, this is some response. When we have like this is, for example, when we input a pulse signal. Yeah, a pulse signal, as you know, is a combination of two-step signal. One is the positive step signal like this from this time until infinity, and the other one is a negative step signal from this value until infinity. When you add, then when you sum the two steps signal, they will form a pulse signal like this. So when you input this pulse signal into a sensor, for example, into a sensing system or instrumentation system, and the sensor cannot respond immediately, there is a T here of delay. This is what we call as propagation delay. of the sensing system. Okay. And when the signal, when the sensor could not follow the waveform of the signal immediately, okay, this is what we call as low frequency roll off. So when the signal like this with a step signal here, the signal has a what do you call it? Decrease, yeah, decrease from its steady state value, supposed to be here this value, but it decreases. Similarly, when going down, supposed to be 0, it goes like this. It goes with a certain what do you call it? Uh, spike, yeah, a spike or a jump. I forgot there is a specific terminology for this, yeah, but it is beyond the actual steady state value. The actual steady state value should go back to 0, but instead it has this spike and then it goes down. It goes toward the steady state value, the 0, slowly. So it cannot follow the response of the stimuli immediately. It has some delay, but the delay is not like this kind of delay, but rather it follows the signal, the stimuli slowly. So this is due to low frequency, what we call as low frequency roll off, because the sensor system cannot follow the high frequency component of the signal immediately. Yeah. So it has basically it has this time constant that makes it slow, that cannot immediately follow the stimuli. Then we have the ringing. Ringing, yeah, yeah. So it has a kind of similar like of high frequency noise, yeah, added to the signal of the sensor, or the output signal of the sensor. While the output is supposed to be flat like this, however, it has this higher frequency ringing, yeah, or higher frequency value imposed to that step value. So here we compare, when we compare three different system, yeah, for example, between sensor A, sensor B, and sensor C, and we see here that sensor C has the narrowest bandwidth compared to the three of them, among the three of them, while A has the widest bandwidth. Yeah, again, we define bandwidth here as the width between the low frequency cutoff and the high frequency cutoff. What is the low frequency cutoff? This is the low frequency region where, yeah, below which the signal amplitude gain is lower than 0.707 compared to the steady state gain. 0.707 here, 0.070 come from the half square root 2, yeah, the from RMS calculation. And between the FL and the FH, FH is the high frequency cutoff. That is where the frequency above which the signal amplitude response of the sensor also drop below the 0.707. Then the frequency width between the low frequency cutoff and the high frequency cutoff, FH, between FL and FH is called as the bandwidth or band pass frequency response characteristic of that sensor or that system. Okay. So if we have a curve here, again, another pulse signal. When we put this into system A, to curve A, the curve A has the widest bandwidth among the three systems. So it means what? It can follow high frequency signal better than system B and system C. That is why here when you put this pulse signal, basically a pulse signal or step signal contains high frequency component, it can follow almost closely to the original signal with only slight delay, yeah, or with some slight time response T1 here before it reach, let's say, 97% of the steady state value. And similarly, also when the signal drops to 0, it can follow closely. This is different than when the signal is inputted into system B and system C. Let's go immediately to system C. And system C has the smallest bandpass frequency response, that has the smallest bandwidth among the three system A, B, C. So as a result, it can hardly follow the pulse signal here, yeah, like this. And even before it can reach the steady state value, it has already this low drop value. Yeah? And similarly, when the signal is dropped to zero, it needs long time before it can follow this dropping. Yeah. So ideally, what you want, of course, is to have a signal with high, uh, with a wide bandwidth, yeah, with a wide band pass frequency response. But of course, this comes with trade-off. Okay, we have discussed about transducer. So transducer is basically a device that converts a primary form of energy to an electrical energy for the purpose of measurement or control. So in transducer, uh, the meaning is more general. While if the meaning is specific towards a transducer that is used to convert or to transform information, the quality of energy, yeah, in from some physical domain or primary form of domain energy into electrical domain of information, then we call it as sensor. So the difference between transducer and electrode, yeah, because in biomedical instrumentation we also use electrode. In transducer, it uses some intervening transducible element to make measurement, while electrode usually directly acquire the signal from the body. Yeah, if you use ECG, EEG, EOG, EMG, you attach electrode to the skin, yeah, to capture the ionic signal, basically IAN, and put it into the electronic signal. Basically, they are of the same energy form. They are of the same information form, which is in the form of charge. Right. The difference is the carrier of the charge. In the in trans in electrode, when you, in the body, the charge is being brought by ions, positive ions, negative ions, as we have learned in previous chapters. Yeah, with negative ions, anions like chlorine, positive ions like potassium and calcium and sodium. While after it reaches the electrode, it is converted into electrical charge, electronic charge. So the charge carrier in the electrode and in the cable, in the wire afterwards, is electrons. Transducer, on the other hand, it has some transducible element, material that can convert the information from one form to another. For example, in pressure transducer, we use the change of resistance of a taut wire element when it is flexed to measure the pressure. In thermistor, we use the change of electrical resistance of some materials undergoing temperature change to measure the temperature. Yeah, so you see here that energy, well, in this particular case, we say as information, yeah, because we are concerned with the quality of the energy itself, not the quantity of energy. The quality is information. Information is converted in thermistor, yeah, from heat, from temperature change into resistance change. In pressure transducer, from mechanical stress, mechanical strain into resistance change. So general in primary transducer, change real world parameter into electrical signal. There is also what we call a secondary transducer, which convert electrical signal into analog or digital signal, or one electrical signal into another electrical signal. For example, like amplifier. We can call amplifier as also a secondary transducer. It converts electrical signal to another electrical signal, but it also does, the signal form doesn't change. The signal energy, the energy form doesn't change, but it does amplification. So it manipulates the information there from the range with a smaller range of value into larger range of value. From millivolt, for example, into volt range. So usually in any sensing system, we don't really use a single transducer or single material that change immediately some form of physical energy directly into a readable electronic signal. Many times we have to use various kind of transducer in between. There's a primary, secondary, 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 until it becomes a usable values. Okay. So let's give an example. So even like in microphone, yeah, microphone usually now is made using uh, capacitive. Yeah, let's say using capacitive. Later we will discuss more. Yeah, this is electrode. This is made from electrode. This is also there is electrode material here. So sound, microphone is used to detect sound. Sound comes as, for example, as a vibration in the air. So vibration itself is a mechanical domain. This vibration, so we call it vibration, will be converted first, yeah, with a transducer to become what? To become pressure, or let's say to become deflection by the membrane here, by the diaphragma. Then afterwards, the deflection is converted. So let's say convert delta here, it become uh, deflected, actually downward due to this vibration, for example. And the deflection delta is converted into delta R, resistance change, for example, by strain gauges. So we have strain gauges attached on the surface of this diaphragm. So afterwards, then this delta R is further converted into what? Into delta V, into voltage change by what we call as a Whetstone bridge. Remember. So here it is not that easy to say which one is primary transducer, because this is still mechanical domain vibration. Deflection is also mechanical domain parameter, while delta R it starts to be electrical domain. This is also electrical domain. Well, we can say that the strain gauge is the primary transducer here, because it is the one the transducer that converts physical domain energy or information, mechanical domain, into electrical domain information in the form of resistance change. Yeah, but before that, there is also actually transducer here. The diaphragm itself acts as a mechanical transducer that converts one mechanical parameter to another mechanical parameter. So in this case, from vibration into mechanical deflection. Okay, I hope this is clear. Then in typical electronic transducer system, wait a moment, let's save this part. Usually, the input or signal or measurement will be converted by the sensor into sensor data, either in analog domain or digital domain. Then it is converted into, it is inserted, inputted into microcontroller for signal processing, and then for communicating to a network or for display. Okay. Many biomedical parameters rely on the measurement of size, shape, and position of the organs and tissue. So that is why then we need displacement transducer. So primary transducer that converts mechanical domain signal or information into electrical domain, depending on the what electrical domain they are converted to, then can be classified into these four. Yeah, for example, can be classified, for example, resistance transducers, which will convert mechanical domain information into resistance change in the electrical domain. Yeah, this an example would be like potentiometer and strain gauges. Potentiometer convert displacement, yeah, into resistance change. Strain gauge convert strain. Remember strain from material, strain into delta R, into resistance change. Inductive transducer converts either motion or displacement into inductance change. Capacitive transducer convert can be displacement, can be pressure change, or what else? Area change, into capacitance change. Piezoelectric transducer converts stress or strain directly into voltage change. And if they are not yet voltage, for example, here in resistive, it is delta R. In inductive, it is delta L. Inductance and capacitive is delta C. Then we need a secondary transducer that converts this parameter into voltage signal. Because you remember that in digital domain, or analog also, we usually work with voltage or current, either way, as the parameter that carries the information. Then when we work with digital, we convert first that analog domain voltage into digital domain, right, in the form of digital binary number bit to represent the information. So in order to do that, we have to convert the resistance change into voltage change. We can use Wheatstone bridge amplifier, and although also use amplifier. Okay. So what is Wheatstone bridge? So this is just an introduction about one of the most common secondary transducer, which also you will be used a lot in your research and also your classes, your practice. Yeah? So Wheatstone bridge, it's basically a kind of combination between two voltage divider. Normally, we can convert a resistance change using a simple voltage divider. So if we have, for example, here voltage source ES, this is grounded, and we have two resistors. Okay. One of them is the sensor whose resistance change with a certain parameter. Let's say it could be. Okay, sorry for the internet problem again. So here, okay, I have to repeat. So let's say a voltage divider. So you have a voltage source. Okay. This is basically, remember, voltage division. One is R1 is X as the sensor. Let's say a strain gives R2 is a constant resistor that we put in series. So here the output is V output. So V out equals to R1 divided by R1 plus R2 times E source. So R1 will change the value as a function of a certain parameter, mechanical parameter, because it is the sensor. So voltage divider is one of the simplest secondary transducer that we can use to convert resistance change into voltage change. The disadvantage of using voltage divider is, however, when when there is no resistance change. So when the stimuli, is zero. So for example, actually, the output will be equals to R1 at 0 plus delta R1. Delta R1 is the change due to the stimuli input. So this is R1 plus delta R1 plus R2 times ES, right? When delta R1 equals 0, which is when there is no stimuli. Yeah. What ideally the offset should be 0, right? In ideal sensor, we want there is no offset. However, if this is 0, what happened is we still have this value times ES. This becomes offset. Now, which is unwanted. We don't want offset. Okay, we don't want offset. So what to do? This is the purpose of voltage, the purpose of Wheatstone bridge. So instead of using a single voltage divider, we use two voltage dividers here, and then we take the difference at the middle between those two voltage division. Yeah, like this. Okay. So then the formula will be the E output, the V output becomes EC minus ED. EC minus ED, right? Equals to the R2 over R1 plus R2 minus E times R4 divided by R3 plus R4. So this is a simplification. So when using voltage Weston bridge, usually we don't want offset when there is no stimuli. So it means when delta R is 0, this value is supposed to be 0. E output is supposed to be 0. This is what the condition what we call as balance Weston bridge or null Weston bridge. Now, in order that this is a 0, so it means that R2 divided by R1 plus R2 should be equals to R4 divided by R3 plus R4. Right? This is condition when we want to be null when there is no stimuli. So let's simplify. R2 R3 plus R2 R4 equals to R1 R4 plus R2 R4. This cancel each other because they are the same, R2 R4. So we obtain R2 R3 equals to R1 R4. So this is the condition of Whetstone bridge. Yeah. So if we look again at the circuit, R2 R3 equals to R1 R4, R2 R3. So the multiplication of the product of the resistor that are opposite to each other, across each other, R2 R3 should be equal. So it should be equal to the other product of the other pair of resistor which is across to each other. R2 R3 equals to R1 R4. So this is the condition if you want to balance the output of the Whetstone bridge such that when there is no stimuli at all from the sensor could be R1, R3, or R2, R4, depending where you want to put the sensor. When there is no offset, when this condition is fulfilled, we obtain E output will be equals to 0 whenever there is no stimuli to the sensor. Okay, so let's take a break. Yeah.